On July 17th, 2026, a 7.3 magnitude earthquake struck Mexico.
Right.
And, if you catch that on the news, it's just so easy to compartmentalize
Oh,
it.
absolutely.
You see a push notification on your phone, you feel a brief pang of sympathy for the people near the epicenter, and then you just swipe it away.
Yeah, you categorize it as an isolated tragedy.
Exactly, just confined to a specific set of coordinates on a map. But the most terrifying part of this specific earthquake wasn't just the shaking in Mexico.
No, it wasn't.
It was the fact that beneath the surface, a massive tectonic gear had just violently clicked into place.
That's a great way to put it.
A gear that is currently pushing an unimaginable amount of strain directly toward California and, honestly, the American Midwest.
Yeah, and that's the thing. The Earth isn't just this collection of static, disconnected rocks floating in space.
Right.
It is a highly sensitive, globally connected, deeply pressurized, closed system.
A giant machine.
Exactly.
Right.
When a disruption happens in one place, the kinetic energy doesn't just magically disappear into the void.
It transfers.
It transfers. It travels through the crust. It literally loads strain onto other parts of the planetary system.
So welcome to the deep dive. Today we are taking a single incredibly dense source. It's a real-time geological analysis live stream broadcast by geologist and geophysicist Stefan Burns, and we are unpacking the staggering implications of that 7.3 earthquake in Mexico.
It's phenomenal analysis.
It really is. So, okay, let's unpack this because our mission today is to treat this like a high-stakes detective story.
I like that.
We're going to trace this invisible web of tectonic energy. We're going to follow it from the Caribbean, up the Pacific coast, into California, across the continent to the Midwest. And then, believe it or not, we are going to trace it all the way out into the solar system.
Yeah, because if we want to actually understand this event, we have to look far, far beyond the epicenter in Chiapas.
Right.
The reassuring narrative that earthquakes are just random, localized bad luck, it simply doesn't hold up when you look at the macro-level data.
It falls apart completely.
It does. To understand where all of this massive seismic energy is going next, we first have to understand exactly what happened at the point of origin.
So let's start right there, at the inciting incident.
Okay.
We have a magnitude 7.3 quake hitting the Chiapas region of Mexico, right down near the Guatemala border.
Right.
And the source highlights a specific geological detail right off the bat. It was incredibly shallow.
Very shallow.
It occurred at a depth of only 18.6 kilometers. Now, when I hear 18.6 kilometers, that sounds pretty deep to me, just as a layperson.
Sure.
Why is that considered shallow, and why does that make it so much more dangerous?
Well, it's all about the thickness of the Earth's crust and how seismic waves travel through it.
Okay.
In continental regions, the Earth's crust can be anywhere from 30 to 50 kilometers thick,
Oh, wow.
sometimes even more under large mountain ranges. Beneath that is the mantle, which is hotter, denser, more plastic.
Right, the gooey layer.
Exactly. So when an earthquake occurs deep down, say, 100 or 200 kilometers deep in the subduction zone, the sheer volume of rock above it acts as a massive shock absorber.
That makes sense.
By the time the kinetic energy of those seismic waves travels all the way up to the surface, a lot of the high-frequency destructive energy has naturally attenuated or faded out.
So it's kind of like hearing a loud party from down the street versus having a speaker right next to your ear.
That's a perfect analogy. But at 18.6 kilometers, you are right in the upper to middle crust.
Which is basically right under our feet.
Practically surface level in tectonic terms. The energy doesn't have enough distance or material to dissipate.
It just punches straight up.
Straight up into the surface, right into the infrastructure where people live. You get maximum ground acceleration, maximum shaking intensity, and maximum potential for structural collapse.
And the source material points out something immediately alarming about this specific location in Chiapas.
Yes, the history.
Right. This 7.3 occurred in almost the exact same geographical spot as a massive magnitude 8.2 megaquake that struck back on September 8, 2017.
Right.
Now, I want to pause here because if you are just looking at the numbers on a page, 7.3 and 8.2 might not sound like they are in totally different universes.
Right, it's just a decimal difference.
It's less than 1 full point of difference,
Right.
but the scale we use for earthquakes isn't like a standard ruler.
No, not at all. It's completely nonlinear. The moment magnitude scale, which geologists use to measure the total energy released by an earthquake, it's logarithmic.
Okay, so what does that mean in practical terms?
So a jump of 1 full point, say from a 7.0 to an 8.0, doesn't mean the earthquake is 1 step stronger. It means the earthquake released roughly 32 times more energy.
32 times? That is insane.
It's a massive leap.
So our source breaks down the specific math for these two Chiapas quakes. The 2017 8.2 released roughly 22 times more energy than this recent 7.3.
Right, or to flip the perspective, this recent 7.3 represents barely 3% of the total energy released by that 2017 megaquake.
3%.
Barely 3. The 8.2 was an absolute monster. Its seismic waves had an amplitude at the actual physical height of the ground displacement that was roughly 8 times higher than the 7.3.
Okay, wait. This is where the detective story really starts for me.
Okay, let's hear it.
In geological terms, 10 years is nothing. It is less than a blink of an eye.
Barely a nanosecond.
Right. So how in the world does a fault system build up enough physical strain to pop off a very powerful 7.3 less than a decade after it just completely emptied the tank with an 8.2?
That is the big question.
I mean, shouldn't that specific piece of the crust be exhausted? Shouldn't it take hundreds of years for the tectonic plates to grind together enough to build that kind of tension back up?
It absolutely should. That is the pivotal question and is exactly what Stefan Burns focuses on in the live stream.
Okay.
Based on the standard model of steady tectonic drift, where plates move a few centimeters a year, about the speed your fingernails grow, there is virtually no reason for this specific junction in Mexico to have accumulated enough strain to release a 7.3 so quickly.
The math just doesn't add up.
It doesn't work. The only way you get a rupture of this magnitude in a fault that recently unloaded is if there was a massive external trigger acting upon it.
Meaning a sudden, violent influx of energy from somewhere else.
Exactly. A violent shift in the larger continental plate system that rapidly, forcibly reloaded that specific fault in Mexico with strain.
And that leads us to what looks like a smoking gun.
The Venezuela event.
Yes. Less than a month prior to this Mexico quake, on June 24, a devastating double sequence struck Venezuela.
That was tragic.
A magnitude 7.2 followed just 39 seconds later by a magnitude 7.5.
The mechanics of that Venezuelan double sequence are fascinating and, horrifying. It occurred on the Boconó Fault. Geologists classify this as a right lateral transform boundary.
Okay, I want to visualize this properly. When you say right lateral transform boundary, what does that actually look like if you were standing on the fault line?
Imagine two massive, rigid blocks of the Earth's crust meeting at a seam. They aren't pushing head-on into each other, and they aren't pulling apart. They are grinding past each other horizontally. If you were standing on one side of the fault line in Venezuela, looking across the crack at the other side, that opposite block of land would be trying to move to your right.
Hence the right lateral part.
Exactly. That's a right lateral transform. The plates are trying to slip horizontally by one another, but rocks don't slip smoothly.
No, they're jagged.
They are jagged, they are heavy, and they interlock, so they get stuck.
The tectonic engine keeps pushing, but the rock won't budge.
Precisely. Friction builds up to unimaginable levels over decades or centuries. The rock physically deforms and bends around that stuck point, which we call an asperity.
An asperity, okay.
Then finally, the friction is overcome. Snap. You get a massive release of pent-up kinetic energy as the blocks violently lurch past each other.
And in Venezuela, we didn't just get one snap. We got two massive releases, just 39 seconds apart.
Yeah.
I can't even begin to imagine what those 39 seconds felt like. You survive a 7.2, the dust is just starting to settle, the buildings that are barely hanging on are groaning.
And then the next one hits.
Less than a minute later, a 7.5 hits and finishes the job. The source mentions that this double sequence creates a much longer, sustained duration of violent shaking, which completely destroys the structural integrity of whatever is built on top of it.
It is a profound human tragedy. The source points out that poor construction practices around the fault trace in Venezuela led to catastrophic building collapses.
Yeah, just horrific.
Tens of thousands of people missing, around 5,000 confirmed dead at the time of the broadcast, with the grim reality that after 3 weeks, trapped under rubble, the death toll is going to be astronomical.
So terrible.
It is. But from a purely geophysical perspective, that immense release of horizontal energy in Venezuela is the absolute key to our mystery in Mexico.
Because the faults don't exist in a vacuum.
Right. We have to look at what these localized faults are attached to. The Earth's crust is a mosaic of massive tectonic plates, kind of like a cracked eggshell. Venezuela sits right on the eastern edge of the Caribbean plate. Now, trace that plate across the map. Mexico, specifically the Chiapas region, sits near the northwestern edge of that very same plate, where it interacts with the Cocos plate.
So they're connected by this one massive piece of crust.
Yes. The Caribbean plate is essentially a giant, solid puzzle piece connecting North America and South America.
So if I'm picturing this right, is it like the transmission gears in a car? Like if one massive cog Venezuela suddenly breaks its friction and turns, grinding violently to the right,
Yep.
the entire solid plate of the Caribbean has to shift with it, which means the cog on the far side of that plate, Mexico, has no choice but to instantly grind forward to accommodate the movement.
Yes, exactly. It's a continent-spanning tectonic domino effect.
Okay.
When you have a massive rupture and physical displacement on the edge of the Caribbean plate in Venezuela, you literally have an entire tectonic plate shifting its weight.
It's a lot of weight.
Unimaginable mass. That massive kinetic energy and physical displacement cannot just vanish. It has to be balanced out on the other side of the system.
The strain has to go somewhere.
It does. And how did it balance out in Mexico? It didn't balance out with another horizontal slip. The moment tensored the physical geometry of the earthquake in Mexico showed it was a reverse thrust earthquake.
A reverse thrust, meaning instead of the ground slipping side to side like in Venezuela, the ground in Mexico literally thrust upwards.
Exactly. Because the Caribbean plate was violently shoved from the east by the Venezuela rupture, it slammed into the plates on the west.
Oh, man.
One block of earth was aggressively pushed up and over another. The Venezuela gear spun sideways, pushing the plate, and the Mexico gear was forced to pop violently upward to absorb that massive influx of strain.
That makes perfect sense.
That's why when this Mexico quake hit, the immediate concern wasn't just shaking, it was a tsunami.
Because when you violently thrust the seafloor upwards, you displace the entire column of water sitting above it.
Yes. And a tsunami is very different from a wave generated by wind.
How so?
Wind waves only affect the very surface layer of the ocean. The water underneath is relatively calm. But when a reverse thrust earthquake permanently heaves a section of the ocean floor upward by several meters, it physically lifts the entire column of water from the abyssal depths all the way to the surface.
The whole thing just shifts up.
Yes, that displaced water then collapses under gravity, sending a massive pulse of kinetic energy racing outward through the ocean at the speed of a jetliner.
The immediate aftermath of that upward thrust in Mexico triggered a tsunami threat for Central America and Mexico. The initial forecasts warned of waves reaching 0.3 to 1 meter above tide level for coasts like Guatemala and Mexico, and smaller wave anomalies stretching all the way from Colombia down to Peru.
Now, a 1-meter wave might not sound like the apocalyptic 100-foot wall of water you see in disaster movies.
Right, it sounds kind of small.
It does, but as the source correctly points out, tsunamis are not surfing waves. They are massive continuous walls of force and momentum.
Right, it's not a wave that crashes and recedes in 5 seconds. It's the entire ocean suddenly rushing inland for 10 minutes straight.
Exactly.
Even a foot or two of that kind of fast-moving, relentless water can sweep you off your feet, lift cars, bash boats against harbor docks, and cause severe local infrastructure damage.
Thankfully, the tsunami threat largely passed without catastrophic coastal inundation this time. But the water was only a fraction of the concern. The source brings up another major geological process that is instantly weaponized by an earthquake of this magnitude landslides.
The live stream actually showed videos of these huge, billowing dust clouds rising from rock slides in the mountains triggered by the shaking.
And this happens because seismic waves drastically exacerbate erosion. Think about a massive cliff face or a steep mountainside. It's already in a constant slow-motion battle with gravity, weathering, and water saturation.
It's just waiting to fail.
You might be structurally hanging on by a thread. Then, an earthquake sends a violent multidirectional vibration through that rock. The friction that was holding the soil and stone together instantly fails.
Wow.
Entire slopes detach and fall. Communities built on or below these unstable cliffs face immense, immediate risk, sometimes far deadlier than the shaking itself.
And to really understand why those cliffs fail and why buildings suddenly pancake, we need to stop thinking of an earthquake as just one generic rumble.
Right, it's not a single event.
The source material dives deep into the anatomy of the shaking itself. An earthquake is actually a sequence of distinct seismic waves running a race against each other through the earth.
Yes.
Let's break down that anatomy, because this blew my mind. When a fault snaps, what is the very first thing that shoots out?
The first wave to arrive is the P wave, or the primary wave. These are compressional waves. They travel incredibly fast through the deep interior of the Earth.
Compressional meaning push and pull.
Yes. Think of a slinky stretched out across a room. If you bunch up one end and let it go, you see a wave of compression travel straight down the line of the slinky.
I can picture that. The coils push together and pull apart in the same direction the wave is traveling. That's a P wave moving through solid rock. It's acoustic in nature.
And the source notes this is the wave that gives you that initial sudden jolt. If you're close to the epicenter, you feel a hard thump, like a truck hitting your house.
Exactly.
But because they are the absolute fastest waves, this is actually the wave that triggers our modern early warning networks. When your phone blurs an earthquake alert, giving you maybe 5 or 10 precious seconds to drop under a table, it's because regional sensors felt that fast P-wave thump and outpaced the slower destructive waves to warn you.
Precisely. The early warning system relies on the time gap between the P wave and what comes right on its heels, the S wave, or the secondary wave.
And the S wave is the one that really starts breaking things.
It is. S waves are shear waves. Unlike the push-pull of the P wave, S waves move the rock perpendicular to the direction the wave is traveling.
So side to side or up and down.
Exactly. If the P wave is pushing a slinky straight forward, the S wave is grabbing the slinky and whipping it violently side to side.
Oh, that sounds destructive.
Very. They move slower than P waves through the crust, but they carry significantly more destructive potential. This is the wave that initiates the aggressive, violent knocking that can literally sweep you off your feet and start snapping structural supports.
Okay, so we've got the initial compressional thump of the P wave, followed closely by the violent side-to-side shear of the S wave. But the source explicitly points out that these two body waves aren't even the main event.
Yeah, they're not.
Then comes the real monster, the surface waves.
This is where the overwhelming majority of the devastation happens. Stefan Burns points out that surface waves contain roughly 70% of an earthquake's total kinetic energy.
70%? Wow.
And unlike the P and S waves, which travel deep down through the three-dimensional body of the Earth's interior, surface waves, as the name suggests, are trapped and travel exclusively along the very top layer of the crust.
Right, where all of our cities are built.
Exactly.
And there are two main types of surface waves that cause all this havoc, right? Love waves and Rayleigh waves. I had never heard of these before, this deep dive. What is a love wave doing to the ground?
A love wave is a purely horizontal surface wave. It whips the surface of the ground side to side in a snake-like slithering motion.
Like a snake. Okay.
What makes it so damaging is that the bottom layers of the crust remain relatively unaffected, but the surface is intensely sheared. Imagine a building, the foundation is being yanked violently left and right, while the top of the building is trying to stay still due to inertia.
It's just going to rip apart.
The structural shear stress is immense.
And then you have the Rayleigh waves, which the source describes in a way that sounds absolutely terrifying to experience.
Rayleigh waves are arguably the most complex and destructive. They roll.
Like an ocean wave.
Very similar. They have a complex, jerky, elliptical rolling motion. As a Rayleigh wave passes through, it moves the ground both up and down and forward and back simultaneously.
That's nauseating to even think about.
It's literally an ocean wave rolling through solid bedrock and dirt.
The live stream showed a video of a massive high-rise building located pretty far from the Mexico epicenter, and the building wasn't jittering or shaking fast. It was dramatically, slowly swaying back and forth, leaning way out over the street and then snapping back.
That's a classic sign.
That wasn't the initial jolt of the P wave. That was the long-period surface waves, the Rayleigh waves, slowly rolling through the continental crust under the city. And what's wild to me is that these surface waves don't just hit a city, knock some things over, and then stop. They just keep going.
The amount of energy we are talking about is hard to comprehend. For a large earthquake, an 8.2 or even a 7.3, those surface waves have so much raw power that they literally circumnavigate the globe.
They go all the way around the Earth?
They travel across the surface of the entire planet.
Yeah.
And they don't just do one lap. For the biggest megaquakes, seismometers can watch those surface waves sweep around the Earth 3, 4, sometimes 5 times before they finally fade.
5 times. That's unbelievable.
The source notes that these colossal events can cause the entire planet to literally reverberate, ringing like a struck bell, for hours afterwards.
I want you listening to really think about that for a second. When you see footage of a building failing during an earthquake, what stands out to you? Because reading this source, I realized it's not just about how hard the ground shakes.
Right.
It's about a physical phenomenon called frequency spectra and resonance. And this was a massive aha moment for me. Can you explain how resonance determines whether a building survives or pancakes?
It is entirely about matching frequencies. Every physical object in the universe has a natural resonant frequency. That is the specific frequency at which it naturally wants to vibrate if you strike it.
Like a tuning fork.
A tuning fork has a resonant frequency. A wine glass has one. And yes, a 40-story skyscraper has a natural resonant frequency. The ground beneath the skyscraper also has one.
And importantly, every earthquake generates a specific frequency spectrum of seismic waves.
Exactly. Some earthquakes generate fast, high-frequency, chattering waves, say, vibrating back and forth 10 times a second, or 10 hertz.
Okay.
Other earthquakes, especially at further distances where only the long surface waves survive, generate slow, rolling, low-frequency waves, maybe 1 or 2 hertz. Now, here's where the catastrophe happens. If the specific frequency of the earthquake waves rolling through an area perfectly matches the natural resonant frequency of a building in that area, you get an effect called resonance amplification.
The source uses an analogy that makes perfect sense to anyone who has ever been on a playground. It's exactly like pushing someone on a swing.
It is.
If you walk up to a kid on a swing and just push them at random chaotic times, they don't go very high, the energy cancels out. But if your pushes perfectly match the natural frequency of the swing, you amplify their momentum with every single push.
Yep, it compounds.
They go higher and higher with very little effort. If a Rayleigh wave is rolling at a slow 2 hertz frequency and a high-rise building naturally sways at exactly 2 hertz, the earthquake is perfectly pushing the swing of that building. The sway gets wider and wider until the steel and concrete simply rip themselves apart.
That is precisely how large structures fail far away from the epicenter. And what makes this even more complex is that this resonance is heavily dictated by the local geology beneath the building.
Right.
The source points to a highly specific historical example to prove this: the magnitude 6.0 earthquake that struck Napa, California back in 2014.
Wine country. Beautiful area, but geologically it's a trap.
Geologically, Napa sits in a natural volcanic basin. Millions of years ago, tectonic forces created a hard rock bowl, and over time that bowl filled up with soft, loose, waterlogged sedimentary deposits from the Napa River.
And seismic waves behave very differently when they hit soft river mud compared to when they travel through solid granite.
Drastically differently. When fast-moving seismic waves leave solid bedrock and enter a soft, mushy sedimentary basin, the laws of physics demand a trade-off.
Okay, what kind of trade-off?
The waves immediately slow down in the soft dirt. But energy must be conserved. So as the velocity of the wave drops, the amplitude, the physical height, and violence of the wave massively increases.
The wave gets taller and more violent to make up for moving slower.
Exactly.
Yeah.
Furthermore, when those amplified waves hit the hard bedrock walls on the far side of the Napa Basin, they don't just pass through.
They bounce.
A lot of the energy reflects back. The waves literally bounce around off the hard rock walls, becoming trapped inside the soft sedimentary fill. The basin essentially acts as an acoustic amplifier, prolonging the violent shaking and creating a horrific resonance effect that destroyed historic masonry buildings across the city.
And the source points out that this specific physical mechanics sedimentary basin amplification is exactly why geologists are so terrified of a major earthquake hitting the Los Angeles basin.
LA is a prime target for this.
Right, because LA is essentially a massive, deep bowl of soft sediment surrounded by mountains. If the right frequency of surface waves rolls into the LA basin, the reverberation, the trapped energy bouncing off the San Gabriel Mountains, and the resulting resonance could be unimaginably destructive.
Which brings us to a terrifying realization about this recent Mexico quake. Because these surface waves travel so far, and because they don't just magically dissipate into the ether, they actively transfer and load their kinetic energy onto other fault systems as they sweep across the continental crust. We have to follow the energy.
We have to track it.
We have to follow this invisible wave of tectonic strain as it moves northward from Mexico up the coast and straight into a region that is, geologically speaking, dangerously overdue for a massive release.
So let's talk about the California question. Is the big one locked and loaded? Because the source lays out a timeline of recent anomalous activity leading up to this Mexico quake that paints a very clear, very concerning picture of strain marching north.
The signs are definitely there.
Before Chiapas even ruptured, we saw some very strange things happen in the Gulf in June.
We did. We saw a clear progression of strain. On June 8th, there was an unprecedented magnitude 6.1 earthquake in the Gulf of Mexico, just northwest of Cuba.
Wow.
The source explicitly calls this an anomalous earthquake. It is the biggest earthquake to ever strike that specific area of the Gulf in recorded history. It shouldn't have happened there, but the plate was being squeezed.
And then on June 30th, just weeks later, a magnitude 6.0 pops off further west and north in the Gulf of California.
Right, stepping right up the coast.
Stefan Burns points out how these two anomalous Gulf quakes form this very neat, structured pattern of strain migrating northward. The tectonic energy from that initial Venezuelan gear shift isn't just loading Mexico, it's pushing outward in a massive arc, sweeping up toward the United States border.
And it is arriving at a fault system in California that is already under immense historical pressure. You have to understand that California's geology operates on a rhythm.
Like a cycle.
Exactly. If you look closely at the historical data spanning the last century, California tends to experience peak periods of high, destructive seismic activity lasting roughly 35 to 40 years, followed by quieter, dormant periods of accumulating strain.
The source points out that the 1980s and 90s were an incredibly active peak period. You had the devastating Loma Prieta quake during the World Series in '89, the Northridge quake that pancaked freeways in '94, a 7.1 in '99, a 7.3 in '92. I mean, California was rocking constantly.
And if you go back roughly 35 years before that active 80s and 90s period, you hit 1952.
1952, what happened then?
1952 was the massive Kern County earthquake. That was a magnitude 7.5. It was a catastrophic rupture.
Okay.
And the source highlights a truly terrifying statistic that 1952 Kern County quake was the very last time California experienced an earthquake of magnitude 7.5 or greater.
Wait, really? What about the big Ridgecrest quake a few years ago in 2019?
Ridgecrest was a 7.1. And again, we have to go back to the logarithmic scale. There is a colossal difference in total kinetic energy release, fault displacement, and destructive power between a 7.1 and a 7.5, let alone an 8.0.
Right, the 32 times multiplier.
Exactly. A 7.1 is severe, but it is not a continental crust-breaking megaquake. California has been spared the true big one for over 7 decades.
So if the rhythm holds, we are currently deep into one of those peak 35-year active cycles right now, but the absolute massive tension-breaking 7.5 plus quake has been entirely absent. It hasn't happened.
Which means the strain on the primary plate boundary, the San Andreas Fault, is astronomical. The source cites recent research by structural seismologists estimating that the accumulated strain on the San Andreas Fault is currently the highest it has been in 1,000 years.
1,000 years. Let that sink in. The rubber band of the San Andreas is stretched tighter right now than at any point in the last millennium.
Uncharted territory.
We are in entirely uncharted territory for modern civilization, and the source details an interesting, terrifying pattern about how California releases this strain. It alternates its ruptures.
It does. The fault system isn't just one line, it's a massive network. And historically, it tends to alternate between ruptures on the faults in the eastern part of the state, like the Mojave Desert area, east of the main San Andreas, and then shifting the burden back to massive ruptures on the western faults, primarily the San Andreas itself.
And the recent history, like that 2019 Ridgecrest 7.1, has all been focused entirely on the east, which implies...
It strongly implies that the pendulum is due to swing back to the west. The eastern faults have accommodated what they can.
The tank is full over there.
Exactly. Every day that passes, every ounce of strain pushing up from Mexico and the Gulf brings California closer to a massive, inevitable shift back to the San Andreas Fault. Are we at that exact flipping point right now? It's impossible to predict the exact day, but the new data strongly suggests the fuse is lit.
Here's where it gets really interesting. Because Stefan Burns didn't just look at broad 100-year historical trends. He dove incredibly deep into highly localized, extremely specific warning signs that occurred precisely when the Venezuelan plates shifted.
Yes, the June 24th double quake in Venezuela didn't just send strain into Mexico. On that exact same day, just hours prior, an historic magnitude 5.6 earthquake struck Ukiah and Willits up in Northern California's Redwood Valley.
And the source notes this is a location that has effectively never had an earthquake this big in our recorded history. It struck right at a critical, complex bend in the northern San Andreas system, a known accumulation point for massive tectonic stress.
The timing is undeniable.
So on the very day the Caribbean plate shifts violently in Venezuela, a completely unprecedented historic quake pops off at a major strain juncture in Northern California. That cannot be a coincidence.
The structural physics tell us it's not a coincidence. It is the physical manifestation of continental strain transfer. And the evidence compounds when you look closely at the Garlock Fault.
Okay, tell me about the Garlock Fault.
The Garlock Fault is a major left lateral strike-slip fault line that runs perpendicular to and directly intersects with the San Andreas in Southern California. Now, the 2019 Ridgecrest quake occurred just north of it, and it loaded a tremendous amount of direct stress onto the Garlock Fault.
Just piling it on.
Right, and the Garlock hasn't had a major stress-relieving rupture in hundreds of years, It is locked tight.
But it's starting to make noise. The source pulled up a 3D fault viewer in the live stream to look at recent earthquake swarms right at that specific Garlock-San Andreas junction.
The microquake.
Right. We aren't talking big destructive quakes. We are talking microquakes of magnitude 4.1 and a 4.3. Most people wouldn't even wake up for those. But the internal mechanics of these small quakes are what terrified the geologists. The source spends a lot of time looking at the moment tensor solutions of these microquakes. Can you explain what a moment tensor actually is and how scientists even measure that?
It's one of the most powerful tools in modern seismology.
Yeah.
When a fault ruptures, it sends out waves in all directions, spherical layers of energy. Seismic stations all around the region record the exact millisecond those waves arrive.
Okay.
By analyzing the first motion of the P wave at dozens of different stations, whether the wave initially pushed the ground up or pulled it down, computers can instantly calculate a 3D geometric model of exactly how the fault slipped underground.
That is wild.
That model is the moment tensor. It's often visualized on maps as a beach ball diagram.
So it doesn't just tell you a 4.1 happened here. It tells you this specific block of rock moved precisely 40 degrees upwards while sliding to the left along a 70-degree fault plane. It gives you the literal geometry of the underground tear.
Exactly. It reveals the physical forces acting on the rock. Now, Stefan Burns analyzes the moment tensors of those two small swarms right at the Garlock junction. The first one, the 4.1, showed an oblique thrust mechanism.
What does oblique thrust mean in plain English?
It means it was a complex grinding motion. A block of the Earth was physically thrusting upwards against gravity while simultaneously sliding horizontally.
So pushing up and sideways.
The rock was being aggressively compressed and shoved up.
Okay, an upward compressed grinding block. And then what happened the very next day?
Just one day later, effectively at the exact same location where the Garlock fault splices into the San Andreas, the 4.3 earthquake occurs. But the moment tensor for this second quake was completely different. It was an extensional earthquake.
Extensional, meaning the rocks weren't pushing together anymore, they were pulling apart.
Yes. The calculated rake angle of the fault slip was near -90 degrees. The tectonic forces completely reversed. The Earth was literally being pulled apart, causing a block of crust to drop down into the newly created space.
In 24 hours.
So in 24 hours, at the precise hyperstrained junction of the Garlock and San Andreas faults, the Earth violently thrust upward under intense compression and then violently ripped apart under intense extension.
The fault is breathing. It's heaving.
It is deforming violently under unimaginable stress. The source argues this isn't just normal random background chatter. This is profound, complex movement of the entire fault zone reacting to immense global strain pushing up from the south.
It's like it's trying to snap.
The rock is trying to figure out how to fail.
I want to offer an analogy for this because I think it's so easy for us to picture fault lines as just simple disconnected cracks in a sidewalk. Like if one crack grows, it doesn't really affect the crack on the other side of the street. But they aren't like that, are they?
Not at all.
When the Garlocks and the San Andreas meet, they aren't two separate lines. The source describes them as being deeply structurally woven together. Think of it like a complexly braided head of hair.
It's a great visual.
You literally cannot tug on one strand of the braid without instantly pulling, tightening, and transferring friction to all the other strands it's woven into.
That's a highly accurate visualization. These faults interlace at depth. They form massive, contiguous fracture zones spanning miles across. When the Garlock fault experiences rapid thrusting and extensional pulling, when that strand of the braid is yanked, it is directly tugging on the already heavily strained strands of the San Andreas.
And that's terrifying.
And the fear isn't just that one strand snaps and we get a localized California quake. The source mentions a growing body of geophysical research suggesting the potential for simultaneous multi-fault ruptures.
Wait, simultaneous ruptures, like multiple megafaults going off at the exact same time?
Yes. Because the systems are braided together, the kinetic energy of one massive rupture can seamlessly transfer and unlock the adjacent system. There's a very real possibility that a massive 8.0 rupture on the northern San Andreas could violently transfer its stress offshore and simultaneously trigger the Cascadia subduction zone up in the Pacific Northwest, or vice versa.
The Cascadia Fault is the one capable of a magnitude 9.0 that would send a massive tsunami into Seattle and Portland.
Exactly. These are structurally connected systems on the edge of the North American plate. A 7.5 or an 8.0 on the San Andreas would be a historic disaster on its own. But if it unlocks a magnitude 9 on the Cascadia Fault simultaneously, It's a scenario that is hard to even fathom in terms of geographic destruction.
And before anyone listening dismisses this as some theoretical Hollywood doomsday scenario, the source pivots to show that this interconnected, continent-spanning, multi-fault rupture event isn't just possible, it has actually already happened.
We have the historical precedent.
The tectonic dominoes have fallen exactly like this before. To prove it, we need to look at history, because as the source wisely points out, while history doesn't repeat exactly, it certainly rhymes. And that brings us to the year 1812 and the New Madrid threat.
If we look back to the geological records and historical accounts of the year 1812, the rhyming is genuinely unsettling. In 1812, Caracas, Venezuela, suffered a devastating double earthquake sequence that completely leveled the city.
Let's pause. Sound familiar? A double sequence in Venezuela. The source estimates the 1812 quakes as a magnitude 7.1 and a 7.4, effectively mathematically identical to the 7.2 and 7.5 double sequence that just hit the Boconó Fault in June 2026.
Exactly the same setup. Now, what else happened in 1812? As that strain transferred across to the plate boundaries, that very same year, massive, highly destructive earthquakes struck Southern California. We had a magnitude 7.5 on the San Juan Capistrano Fault and a 7.1 occurring just 2 weeks later.
So Venezuela double quakes, the strain moves, and California gets obliterated.
Exactly.
The tectonic dominoes fell in 1812 exactly as the current microquake data suggests they are lining up to fall right now. But 1812 holds one more massive, terrifying surprise, because the energy didn't just stop at the Pacific coast. The continental plate was squeezed so hard that the energy transferred directly into the heartland of America. 1811 and 1812 were the years of the infamous New Madrid mega earthquakes.
The New Madrid seismic zone is located smack in the middle of the American Midwest, spanning across states like Missouri, Arkansas, Tennessee, Kentucky, and Illinois. And seismologically, it is a very different beast from the San Andreas.
How so?
The San Andreas is an active plate boundary where two plates grind past each other. New Madrid, however, sits entirely within the interior of the North American plate. It is an intraplate fault zone. It's built upon a geologic feature known as the Real Foot Rift.
I had to look this up because it's fascinating. A rift is basically an ancient failed attempt by the continent to tear itself apart, right?
Precisely. Roughly 750 million years ago, tectonic forces began to literally pull the North American continent apart right down the middle. The crust thinned, massive faults formed, and a deep valley was created. But the tectonic forces eventually shifted, and the continent failed to split.
It just gave up halfway through.
It stayed whole, but it left behind this deeply scarred, structurally weakened, chewed-up fault system buried deep underground. The crust there is fundamentally compromised. And what makes the New Madrid Fault so uniquely terrifying isn't just the rift itself, it's what currently sits directly on top of it.
The Mississippi River.
Yes, the Mississippi River Basin. Over millions of years, the river has flowed over this sunken rift valley, depositing hundreds of feet of soft, water-saturated sand, mud, and river sediment directly on top of the fault system.
Oh man, we're back to the sediment problem.
Now think back to what we discussed about the Napa earthquake in 2014. We talked about how sedimentary basins drastically amplify seismic waves, slowing them down and increasing their violent amplitude. Now imagine a magnitude 8.0 earthquake detonating directly underneath the massive, wet sedimentary fill of the mighty Mississippi River.
The host of the live stream doesn't mince words when talking about this. He says it's all just sediment there. It's going to shake like a son of a gun. The ground wouldn't just shake. It would undergo a process called massive liquefaction.
Liquefaction is one of the most destructive phenomena in geology. When water-saturated, loosely packed sediment is subjected to intense, prolonged seismic shaking, the water pressure between the soil particles suddenly increases.
The water just pushes the dirt apart.
The soil loses all its sheer strength and stiffness. It stops acting like solid ground and literally begins to act like a dense, viscous liquid. Quicksand.
The historical accounts from 1812 are almost unbelievable. Eyewitnesses reported the ground rolling in visible waves several feet high. They reported massive fissures opening up and spewing geysers of water and black sand into the air. Entire towns simply sank into the liquefied earth.
It's apocalyptic.
Massive tracts of forest were snapped in half. The seismic uplift actually caused a section of the Mississippi River to temporarily flow backwards, and the sheer displacement of the crust created massive new bodies of water, like Real Foot Lake in Tennessee, literally out of nowhere. And the shaking was so intense that it reportedly rang church bells in Boston over 1,000 miles away.
And this wasn't a one-off fluke of history. It wasn't an anomaly. The source details the paleoseismic recurrence intervals for massive megaquakes in the New Madrid zone.
Right, they dug trenches to figure this out.
By digging trenches and carbon dating layers of liquefied sand, geologists have mapped out a terrifying rhythm. The geological record shows huge, crust-breaking events occurring around 2350 BC, then 1620 BC, 300 AD, 900 AD, 1450 AD, and finally 1811 and 1812.
Okay, let's do the math on that. If you look closely at those intervals, they aren't stable. The time between megaquakes seems to be actively decreasing. The gap is getting shorter.
It does appear that way. Based on that short geological record, the average recurrence interval seems to be dropping to somewhere around 210 years.
Well, 1812 plus 210 years is 2022, so we're currently, right now, past the statistical window for a New Madrid megaquake.
We are squarely inside the danger zone. And remember those powerful seismic surface waves from the recent Mexico thrust and the anomalous Gulf quakes? The source shows how that kinetic energy didn't just sweep west to hammer California. The strain propagated north and east across the continental plate, heavily loading tectonic tension directly into that deeply buried, ancient real-foot rift fault system.
Okay, I have to push back here for a second because this is a terrifying picture, but it feels a bit unbalanced.
How so?
With California, you laid out all these very clear, real-time warning signs, the 5.6 in Willets, the weird microswarms on the Garlock, the moment tensors actively thrusting and pulling apart. The data in California is noisy and incredibly active. But New Madrid has been completely quiet.
That's true. It has.
We aren't seeing daily swarms in Missouri or Tennessee. Doesn't that complete lack of small earthquakes mean we are relatively safe there for now? Doesn't the silence mean the strain just isn't there yet?
It is a very logical assumption to make. We associate earthquakes with danger. But in geology, silence is often the most dangerous sound of all.
Why is silence dangerous?
A fault that is slipping in small microquakes is relieving a tiny bit of pressure. A fault that is completely silent is a locked fault. It means the friction is holding, and 100% of the strain is accumulating without any release. However, the source explicitly addresses this fear of a sudden, zero-warning megaquake.
Okay, so we get a warning.
The structural geology suggests that before a massive 1812-style New Madrid 8.0 goes off, we will not be taken entirely by surprise.
We will see foreshocks.
Yes. Because the fault system is so massive, and because it is buried under so much compressive weight, it is highly likely that the rock will begin to fracture and slip in smaller increments before the entire ancient rift unzips. We will likely see foreshocks in the magnitude 4, 5, or even 6 range.
So bigger than those microquakes in California.
Much bigger. Those initial moderate quakes will be the localized failure of specific asperities, the sticking points creating the initial structural fractures that allow for the catastrophic larger slip to occur days or weeks later. So the absolute moment we see an anomalous magnitude 5 or 6 in the Midwest, the alarm bells for a New Madrid megaquake will be deafening.
Okay, so we've established the Earth's plates are perfectly interlocked. Venezuela shifts horizontally. Mexico thrusts violently upwards. The Gulf anomalies map the path. California strains under a 1,000-year peak, and the Midwest gets loaded with tension.
A perfect chain reaction.
It is a flawless, deeply terrifying mechanical system. But, it is incredibly easy for us to think of these historical rhyming patterns as strictly an earthbound phenomenon, just rocks pushing against rocks in a closed loop.
But it's not a closed loop.
No. Stefan Burns takes this analysis one massive step further. If we want to truly understand why these major tectonic shifts cluster together in time, why 1812 was so active, why 2026 is becoming so violently active, we have to look up from the dirt. We have to look at the sky. We have to look at extraterrestrial triggers.
This is where the analysis becomes truly holistic, moving from the realm of geophysics into astrophysics. Because to understand the Earth's mechanical energy systems, you have to acknowledge where almost all of that physical energy originates.
Right.
The source points out a staggering foundational fact that is easy to forget. 99.999% of all energy coming into the Earth's system comes directly from the sun.
Right. The host breaks it down to a physical quantifiable measurement, 1,362 watts per square meter on average, constantly bombarding the planet.
It's a huge amount of energy.
To put that in context, if you had a 100% efficient solar panel that was exactly 1 square meter large, it would pull in enough energy every second to run roughly 4 standard kitchen refrigerators.
Just in 1 square meter.
Now, multiply that single square meter by the entire surface area of the Earth facing the sun every single second of every single day. The sheer volume of kinetic, thermal and electromagnetic energy being pumped into our planet is incomprehensible.
And that massive influx of solar energy isn't static. It's not a constant hum. The sun has highly dynamic cycles. The source introduces a concept called the Gleisberg cycle, which is an 80 to 100-year long-term solar rhythm. It tracks the strength and frequency of sunspots, solar flares, and most importantly, the overall strength of the sun's polar magnetic field.
Just like Earth has a north and south magnetic pole, the sun has a massive polar magnetic field that wraps around the entire solar system. Yeah, the data correlation the source presents here is what really blew my mind.
It's fascinating.
He overlays historical earthquake data, but specifically only looking at the absolute biggest crust-shattering megaquakes, magnitude 8.5 to 9.5, and above he overlays that data on top of the graphs of solar cycles.
And the correlation is undeniably striking. It jumps off the page. The largest, most destructive megaquakes in recorded human history, the 1952 Kamchatka 9.0, the 1960 Valdivia quake in Chile, which was a massive 9.5, the 1964 Alaska 9.2, the 2004 Sumatra 9.1 that caused the Boxing Day tsunami, and the 2011 Tohoku quake in Japan.
Absolute worst ones.
These colossal events heavily consistently correlate with periods when sunspot activity and the sun's polar magnetic field strength are incredibly weak.
Okay, I need to understand the physical mechanics here. Why does a quiet, low-energy sun equal a violent, highly active Earth? What is the actual link?
It has to do with how the sun's magnetic field interacts with the Earth's magnetic field in the physical crust. During a solar maximum, when the sun is highly active with lots of sunspots and flares, the sun's polar magnetic field actually drops to near zero.
So it turns off.
It becomes chaotic as it prepares to physically flip its magnetic poles. But what Stefan Burns' data highlights is a long-term, decades-long structural collapse. The overall baseline strength of the sun's polar magnetic field, even during its relatively strong periods, has been steadily decreasing since about 1975.
Wow.
And precisely as that solar magnetic shield has weakened and collapsed over the last 50 years, the global frequency of massive magnitude 8+ megaquakes has drastically increased.
It's an inverse relationship. When the sun's magnetic shield drops, more cosmic rays penetrate the Earth's atmosphere, atmospheric pressure systems change, and some geophysicists hypothesize that changes in the Earth's magnetic field directly alter the rotation speed of the planet by fractions of a millisecond.
And that's enough to cause chaos.
When a spinning top changes speed even slightly, the crust flexes. The friction between the mantle and the crust shifts. The Earth is a spinning engine, and the sun controls the throttle. And the sun isn't the only celestial body pulling the strings here. The source introduces lunar and direct gravitational factors, specifically king tides and supermoons.
Yes. The timing of the Mexico quake is critical here. On July 14, just 3 days before the 7.3 reverse thrust in Mexico, the Earth experienced a new moon that was in a supermoon position.
Meaning the moon's elliptical orbit brought it significantly closer to the Earth than average. It was at perigee.
Exactly. And gravity is dictated by mass and distance. When the moon is closer, its gravitational pull on the Earth is significantly, measurably stronger. We see this most visibly in the oceans.
The tides.
The source showed footage of massive king tides, huge tidal swells that cause coastal flooding in places like Mission Beach in San Diego, where the ocean was literally pushing up through the city's storm drains.
Yeah.
But the moon's gravity doesn't just pull on liquid water, it pulls on the solid, rocky crust of the Earth itself.
Which geologists call earthotides.
Yes. The gravitational tug of a supermoon literally causes a physical, vertical displacement of the continental crust. It can stretch the rock upwards by several centimeters. It physically flexes and stretches the tectonic plates.
I didn't know rock could even stretch like that.
Oh.
Now, under normal circumstances, the rock just flexes and settles back down. But when you have highly strained, fully locked fault lines like the Boconó Fault in Venezuela or the subduction zone in Mexico that are already sitting right on the razor's edge of mechanical failure, the added gravitational pull of a supermoon can absolutely act as the final straw that breaks the structural camel's back.
I want to be careful here because I know we are about to take one more massive step into the cosmos, and I know to the layperson this can start to sound a bit like astrology, but we are not talking about star signs. We are talking strictly about astrophysics, planetary mass, and gravitational mechanics.
Pure physics.
The source details something called planetary geometry, and right now our solar system is in a bizarre, mathematically precise configuration.
It is a historic configuration. Stefan Burns describes a multi-thousand-year basket configuration currently occurring between the major gas giants of our solar system. We are looking at precise 60-degree angles, which astronomers call sextiles, between Jupiter, Uranus, Neptune, and Pluto.
And as a direct geometric result of those 60-degree angles, we currently have a direct Pluto-Jupiter opposition. They are lined up directly across the solar system from each other, with the sun in the middle.
And while these outer planets are incredibly far away, their sheer mass is astronomical. Jupiter is a gas giant, so massive it doesn't even orbit the center of the sun. Jupiter and the sun orbit a shared center of gravity just outside the sun's surface called the barycenter.
That's how heavy it is.
When these massive planetary bodies align in these rare, precise geometric configurations, they create incredibly complex gravitational and magnetic wave interactions that ripple across the entire solar system. They slightly alter the solar barycenter, which can trigger solar flares, which in turn violently impact the Earth's magnetosphere.
Earlier, I asked you to imagine the interconnected fault lines in California as a braided head of hair. Now I want you to zoom way, way out. Imagine the entire solar system as a giant, incredibly complex game of 5G chess.
It's a good way to picture it.
The Earth isn't just floating in an empty void. It is suspended in a highly active web of immense magnetic fields and gravitational forces that are constantly, relentlessly tugging, pulling, stretching, and squeezing the crust we live on. When Jupiter and Pluto align and shift the barycenter, when the sun's magnetic shield drops and alters the Earth's rotation, and when the supermoon pulls directly on the rock, it's a cosmic squeeze on a planetary scale.
And that cosmic squeeze translates directly into localized tectonic strain, which brings us to the final critical piece of the puzzle. With all these cosmic forces squeezing the planet from the outside and all these tectonic dominoes falling from Venezuela to Mexico on the inside, all that pent-up kinetic energy has to go somewhere. The ultimate question for geologists is, where are the relief valves and who is next in the line of fire?
Let's talk about those relief valves. We have mapped out where the strain is building, the 1,000-year peak in California, the overdue Reelfoot Rift in New Madrid. But does the Earth have natural ways of safely venting this immense tectonic pressure before a fault catastrophically snaps? A viewer in the live stream asked Stefan a fascinating question. Do volcanoes take pressure off faults?
And the answer is unequivocally yes, they can. Volcanoes act as massive thermal and mechanical pressure release valves for tectonic strain. The source uses a brilliant, highly visible geological example to prove this, the axial seamount.
The axial seamount. This is an underwater volcano, right?
Yes, it is a very large, highly active submarine shield volcano situated directly on the boundary of the Juan de Fuca Plate off the coast of the Pacific Northwest. Now, if you look at a seismic map of that plate boundary, you'll see a massive, high-frequency cluster of earthquakes occurring all along the fault line.
Just a wall of dots.
It's a highly active zone. But right in the middle, exactly where that massive volcano sits, there is a distinct, highly noticeable seismic gap.
A seismic, meaning there are almost zero earthquakes happening right there. It's a dead zone for shaking.
Exactly, because the volcano is doing the work. It is constantly, steadily venting the tectonic energy from the grinding plates through magma displacement, thermal heat release, and crustal expansion.
It's bleeding off the pressure.
The tectonic strain never has a chance to build up in the solid rock and cause a major mechanical snap. It's being safely, continuously vented into the ocean as heat and new crust.
But the relationship between earthquakes and volcanoes goes both ways, doesn't it? Volcanoes can safely vent strain over time, but massive, sudden earthquakes can also violently trigger dormant volcanoes?
They absolutely can, and they frequently do. The source notes a very strong, heavily documented historical correlation between the largest tectonic megaquakes and massive volcanic eruptions occurring in the exact same region, usually following a delay of 1 to 3 years.
Why the delay? What is the earthquake actually doing to the volcano?
Think of a magma chamber deep underground as a highly pressurized bottle of soda. When a magnitude 8.2 or 7.3 earthquake hits, it sends violent seismic waves through the crust. These waves physically fracture the surrounding rock, literally opening new vertical pathways for the pressurized magma to ascend.
Wow.
Furthermore, the sheer mechanical shock of the earthquake can destabilize the gas suspended in the magma chamber, causing it to rapidly expand, just like shaking that soda bottle.
So it's bubbling up.
So an earthquake in Mexico doesn't just threaten cities with immediate shaking, it can fundamentally alter the plumbing of nearby volcanoes, priming them for massive explosive eruptions in the near future.
So if volcanoes are the relief valves, but they aren't enough to stop the dominoes entirely, who is the next domino? Based on all the data Stefan Burns analyzed in this source, the Caribbean plate shifting, the Mexico thrust accommodating it, The Gulf anomaly is mapping the northward strain. What is the most immediate danger zone forecasted?
Based purely on the structural connections and geometry of the Caribbean plate. The source points a giant, flashing red arrow directly at South America, specifically the nations of Colombia and Ecuador.
Let's connect those geographical dots for the listener so they can picture why. Why Colombia?
Picture the map of the Caribbean plate again. It's a massive, irregularly shaped polygon. You had the massive 7.2 and 7.5 right lateral strike-slip rupture in Venezuela on the eastern edge. That pushed the plate west.
Okay, pushing to the left on the map.
But then you had the 7.3 reverse thrust in Mexico on the northwestern edge, absorbing some of that push. Colombia sits squarely on the southwestern edge of that exact same plate, right in the middle of the tectonic crosshairs.
They're caught in the middle.
It borders the exact geologic systems that have just violently displaced massive amounts of crust. The plate is torquing. The source explicitly warns that a magnitude 6.5 or 7.0 plus earthquake is highly likely in the Columbia region in the coming weeks or months. It is the next logical mathematical point of structural failure in this cascading system.
So, what does this all mean? We have covered an immense amount of ground today. We've talked about solar maximums dropping magnetic shields, Jupiter and Pluto shifting the barycenter of the solar system, the 1812 New Madrid liquefaction sinking towns in the Midwest, and tectonic transmission gears grinding in Venezuela.
It's a lot to process.
It is. For the listener who is sitting in their car or walking their dog or doing the dishes right now, what is the ultimate takeaway? I think it's absolutely vital to emphasize that while we as humans cannot stop these tectonic gears from turning, understanding this massive interconnected planetary system is the difference between helpless panic and educated preparedness.
Precisely. If you only look at the world through the narrow lens of the daily news cycle, an earthquake is just a random act of violence. But the Earth is a dynamic, living mechanical system. It breathes, it stretches, it accommodates stress, and it shudders. The magnitude 7.3 in Mexico isn't just a random data point. It is quite literally a measurable heartbeat in a much larger, globally connected circulatory system of kinetic energy. When we learn to track that energy from the magnetic fields of the sun, to the gravitational pull of the moon, to the anomalous quakes in the Gulf, all the way to the strained faults in California, we stop being blind victims of random chance. We start becoming observant, aware inhabitants of a complex living planet.
It is truly incredible to think that a violent event on a random Tuesday morning in Chiapas, Mexico, is intimately, physically, mechanically tied to the magnetic poles of the sun, to the historical ghosts of 1812, and to the very ground beneath our own feet.
It fundamentally changes how you look at the world. You realize everything is touching.
It really does. But before we wrap up today's deep dive, I want to leave you, the listener, with one final, deeply provocative thought. I want you to mull this over, and it builds entirely on a specific brief detail mentioned in the source material. The source pointed out that over millions and millions of years, an unfathomable amount of raw solar energy was sequestered deep into the Earth's crust as hydrocarbons. We know them today as fossil fuels.
Yes. Oil and coal are essentially millions of years of trapped, concentrated sunlight, deeply buried and pressurized in the crust.
Right. And if we accept the premise that 99.999% of the Earth's energy comes from the sun, and human beings are currently digging up and rapidly combusting millions of years worth of that deeply stored, incredibly dense solar energy, and we are doing it in the absolute blink of a geological eye, how is that sudden, massive release of ancient trapped energy altering the physical strain dynamics of the planet itself?
That's a massive question.
Think about it. We are taking mass out of the crust, burning it, and releasing it as heat into the oceans and pressure into the atmosphere. We always talk about fossil fuels in the context of changing the climate and heating the air. But if we are fundamentally altering the mass, pressure, and energy balance of the entire planetary system, could that rapid release of ancient solar energy be physically changing the structural vibrations of the crust we walk on? Could the redistribution of that mass and heat be loading the tectonic dice?
That is a staggering, deeply unsettling question to consider from a geophysical standpoint.
Yeah.
You were talking about altering the thermodynamic engine of the planet.
It's something to think about the next time you look down at the solid ground beneath your feet. We started this whole deep dive by talking about the desire for a clean, precise diagnosis. We want an X-ray with a clean white line. But the truth is, the geological picture is infinitely more complex, infinitely more muddy, and far more interconnected than we ever wanted to believe. We are living on the outer shell of a massive spinning engine, and every single part is moving. Stay insanely curious, keep looking past the surface, and keep exploring. We'll catch you on the next one.